So down to the last day. What I plan to do today is review the entire semester to the extent I can. Before I even start, a couple things. The final exam is on the 9th, which is a Tuesday. Correct me if I'm wrong. 9 to 12. It's twice as long as a normal midterm. So 60 questions. You do not need 3 hours to complete it. There will be no one here at 3 hours except for maybe somebody who overslept until 11:30, which happens. Yeah, most of you will be done in less than an hour, or give or take. What else? I encourage you, as always, to review the old exams. Be aware that some of the questions of the old exam refer material I no longer cover. For example, about iron and steel and glass and a few other things that just aren't part of this semester's material. What else? Orion, don't worry about Orion. As long as you've just taken a shot at a lot of the questions, excess of 100 and actually tried, you're good. It's been a nightmare for all of us. So I turn in bad reviews to the website people, say, no, this is too hard to deal with. My office hours will continue until the exam. The evaluation, course evaluation, those who haven't done it, it's due, I believe, today's Monday, Wednesday, May 3rd, shortly before midnight, I think is when it's hard, it's a hard deadline. If you miss it, I can't fix it. It's not my course evaluation in the sense that I run it. It's the university runs this. So if you do it before the deadline, I drop your lowest probability set score. That's my incentive, just to have you all please complete it. Any other logistical things that yeah. The exam is here, yeah. Bring a pencil, it's a bubble sheet, usual sort of thing, just twice as long as the midterm. Yeah.
Since the finals cumulative, study the other, like the old midterm to adjust.
Yeah, thanks. The final is cumulative. It's sort of, the way I view it is it's two 30-question pieces. 30 questions are the third midterm, and the other 30 questions are open season on anything. That's approximate, So do go back to the old material. And in my review, I'll do the whole, I'll remind you what we learned way back when. Other questions? Yeah. The old exams, are they similar format, 30? Yeah, pretty much. If you go back far enough, you may encounter exams that the final exam was 80 questions at one point. I had one midterm, one final. So things changed a little bit. But otherwise, same idea. Anything else? All right. So just to remind you where we started, first topic was skating. And that was all about inertia. So there's sort of the introduction to the idea, for example, the key idea, that forces don't cause motion, they cause changes in motion. And more explicitly, forces don't cause velocity. If you're moving, if you have a velocity to start with, you keep moving in the absence of forces. Forces are necessary to cause accelerations, which is changes in velocity. The deep underlying reason for why sort of inertia works like this is really conservation momentum. If you've got momentum, you can't stop moving. You have to carry the momentum with you until you transfer it somewhere else. And if nobody pushes on you, you don't transfer it. So the three famous conserved quantities of motion are sort of one of my favorite thing to ask questions about. And as I say that, I should remind you that obviously can't rehash the entire stories of each of these topics. Only what I consider sort of the physics high points, and that's probably what I'm going to test you on, is the physics high points. They may not be quite the same ones I pull out of the top of my head or otherwise right now, but they're going to be similar. I'm not going to go testing you on, some of the Orion questions, one of them was like, which has higher energy, the S, D, F, P orbitals? Like, that was not a good question. I didn't do that. It is naive. It's a flawed question in 100 ways. Anyway, we're going for the main points. So skating, what's it about? It's really about these basic laws of motion. The fact that if nothing pushes on you, you coast. You move at constant velocity. Falling balls, first force, the force of gravity. So objects experience a downward force that is exactly proportional to their mass, which by itself is a remarkable thing. Other forces aren't related necessarily to mass. For example, the forces between charges have nothing to do with mass. So here it is, you're pulled down with a force proportional to your mass, and because of that semi-coincidence, everything falls together. The high mass objects that are falling also have large downward weights. So that perfectly compensates one for the other. Strong force, big mass resisting the force. What else about falling? Things cover more and more distance with every passing second they've been falling because they are accelerating. The force, again, causes acceleration. And even if something's going up, it can be falling. It's just the downward acceleration due to gravity is the only thing going on. And happens to be heading up, but it's still falling. All right, that's falling balls. Ramps. Ramps, in part, was bringing yet another force into the story, what I call support forces that are exerted perpendicular to surfaces. When two surfaces try to pass into each other, they push apart with forces perpendicular to surfaces, and those are the support forces. And in a ramp, you get this interesting arrangement where a wagon on a ramp experiences, well, at least two forces simultaneously. It's weight down, because you can't get rid of that, and a support force in the wagon that's up at some angle, and those two forces don't cancel. And so there's a net force on the wagon, and it tends to accelerate downhill, unless you begin to push it up and add another force to it. And so you can do things like you can push it uphill to great height with a gentle force, but that gentle force doesn't come, there's a price. You can take a wagon up a hill instead of just simply lifting the wagon up the hill straight up on a ladder, but you have to travel farther. And that part of that story was the reason I did it is to talk about energy. Yet another conserved quantity. You exchange energy with things, but you can't create it or destroy it. You can hide it because energy has various forms, including these potential forms that are stored in forces. But you can't make it or destroy it, so you have to, you move it around. It moves around among things, and you can learn a lot from watching it move, and we did for the rest of the semester. Energy going from here to there, from one form to the other, shuttling around. Mechanically, it's moved by the process known as work, doing work. And doing work is a very specific activity, and I've never gotten a good language to describe it, but I think of it as a microscopic story. Don't get distracted by the stuff outside the center of the story. You're looking, if you want to see whether the person who is carrying a briefcase up in an elevator at constant velocity, and you should know this question. You may see it yet again. Person going up in an elevator at constant velocity, the net force on the person is 0. The net force on the briefcase is 0. The person is just sitting there, could be totally asleep. The question might well ask, is the person doing work on the briefcase? And hidden in that statement is the person doing positive work on the briefcase? Work is always positive unless you say otherwise. So the person doing positive work on the briefcase, it's a microscopic story. Don't worry about the person being in an elevator. Don't worry about even being a person. Just look at the hand. The hand is pulling up on the briefcase. If it didn't, the briefcase would fall. So issue 1, is there a force exerted by the person on the briefcase? Yes. Issue 2, in doing work, does the briefcase move a distance in the direction of the force? Yes, it's moving up. Force is up, the briefcase moving up. The person is doing work on the briefcase. Is that okay with everybody? If you don't use that rule, really, the counting goes all crazy. You lose. If you try to say, well, no, it's the elevator doing the work. Well, maybe what about the motor running the elevator? What about it goes on forever? You have to look at the point where somebody's pushing, is it moving? Right there. Nothing else matters. All right. That's story of work. Seesaws was a story, sort of a rehashing of the story of the laws of motion, but now in the context of rotation, spinning around. And they're pretty similar. You don't have to twist something to have it be moving. Things, torques, the fancy name for a twist. Torques don't cause rotational motion. They cause changes in rotational motion. It's a little more complicated because things that can change shape can mess with their rotation. But in general, something that is rotating continues to rotate unless something exerts a torque on it. You don't need to exert a torque on it to keep it moving. It's inertia keeps it moving. Secretly underlying inertia in all this is angular momentum. That's really where the deeper story. Wheels. Story of friction. I just bring in yet another force. Frictional forces are distinguished from support forces because they act along surfaces rather than perpendicular to surfaces. And the other thing about frictional forces is they can turn useful energy into thermal energy, and often do. Things that actively slide across one another, some of the energy that was in the motion, and typically as kinetic energy, gets ground up into thermal energy, which is a useful and important part of life. Thermal energy is, if we didn't have it, we would be motionless. We would be rather cold. So we have to have thermal energy, but it's often many things in modern life are designed to try to avoid turning useful energy into thermal energy as much as possible. And if they do make thermal energy, they do it as efficiently as possible. All right? Last topic in that early section was bumper cars, which was really the story about moving around momentum and angular momentum. I'll remind you that momentum, to distinguish momentum from energy. Energy is a non-direction quantity. It's what's called a scalar. It's just an amount. 10 units of energy, 100 units of energy, a deficit of 10 units of energy. No direction associated with it. It's the conserved quantity of getting things done. Momentum is a conserved quantity of moving. It's all about motion, and it does have a direction. It is a vector quantity, and the vector is pretty straightforward. You know, if I'm moving to the left, my momentum is to the left. It happens to be my mass times my velocity. Yeah, John.
I think it's on exam 1, but there's the question about energy and momentum. It was like, tennis ball is thrown at the wall, and you throw something at the wall.
Yep. Yeah. Yeah. So when something bounces off the wall, so I've asked questions. You'll see them in exams you've already taken, exams in the past. When something bounces off of a wall, for example, a ball. The ball, in traveling in there, carried two separate conserved quantities with it. And the accounting for those conserved quantities is separate but important. When the ball hits, it's carrying energy, for one, kinetic energy, the energy associated with its motion. And to get rid of that energy, it would have to transfer it to the wall. You can't destroy it. To transfer it to the wall, it doesn't work. Well, the wall won't move. At least for practical purposes, the wall's immobile. And therefore, or immovable. Therefore, when the ball hits it, it does no work on the wall, and the ball retains its energy. It bounces back. It has to keep going. The alternative is it can grind the energy up into thermal energy. So there are balls that go splat. You know, they hit, but where the energy is still in the ball, it's just been turned into thermal energy. The ball literally got hotter. So that's part one. Part two is the momentum. For the ball, it's carrying momentum toward the wall. When it hits the wall, if it gives up all of its momentum, 100% of its momentum, it comes to a stop. So it was heading to the right, say, and it comes to a stop. It's no longer heading right at all. Well, if it still has energy, and that energy isn't in thermal form, then it's got to move. Then it needs to get some momentum back again. And what most of the balls you encounter do is when they hit the wall, they don't stop. They bounce back. So a lot of the energy remains in them. In fact, in principle, all of the energy remains in the ball. What about the momentum? It went from heading into the wall, toward the wall, to heading away from the wall. That's a huge change in momentum. The ball went, because momentum has a direction. And momentum to your right is completely different from momentum to your left. In fact, one is the negative of the other. So if you give all of your rightward momentum to the wall, you come to a stop. If you give twice your rightward momentum to the wall, a huge amount, you end up going the other way just as fast. Is that okay? So a lot of bouncing things give none of their energy to the thing they bounce off of. But they do give it momentum, and they give it a lot of momentum. How much? More than they had. Momentum is transferred by impulse, force times time. There's no, the object that you hit doesn't have to move to give it momentum. You just have to exert a force on it, and time has to pass. And so a ball bouncing off a wall pushes on it for so long that it actually ends up going backwards. Yep. Yep. Yeah, a ball hitting a hoop in a basketball. Yes, if it fails to move the hoop, the ball's still got all its energy. So there are lots of games, lots of sports games and games at amusement parks and stuff like that, where the fact that it's hard to give energy to something that won't move makes the game difficult. Momentum's easy to transfer. I can transfer momentum everything I hit. But transferring energy is a lot harder because it's got to move. Is that okay? All right, so at that point, sort of having worked through the basic laws of motion type stuff, we jumped off into the world of electricity and magnetism. First story was about electric charge and static charge. And the observation that in nature there are two types of charge, at least at the naive level, positive and negative. And like charges repel, opposite charges attract. A little more deep level, at least I told you, the charge is really just one quantity. It's a conserved quantity. You can have positive and negative amounts of it. So negative charge is an absence of positive charge. The bigger the negative charge, the more absent there is of positive charge. Yeah? Test charges are defined as always being positive charges. So the only thing distinguishing a test charge from just any old positive charge is the test charge isn't supposed to affect anything else. It doesn't make its own electric field. It just watches other ones. So if you have positive and negative charges around, they exert forces on one another. Likes repel, opposites attract. The forces get stronger as they get closer, and they get stronger dramatically. The forces are proportional not just to the one over the distance, they're proportional to 1 over the distance squared. So as you have the distance between two charges, the force goes up by a factor not of 2, but a factor of 4. All right? Already by then I started talking about voltage. There's energy stored in the forces. Potential energies are all energies that are stored in forces, and so you can store energy in the electrostatic forces between charges. And that energy, electrostatic potential energy. And if you look at how much energy a portion of charge has when it's in a particular location, so it's a feature of locations. If at this location a little bit of charge has a lot of energy, and a little bit of charge is by definition a positive amount of charge. Again, it's another one of these things. If I don't say negative, it's positive. Charge is always positive unless you say otherwise. So if putting a little bit of charge, positive charge here, means that charge has lots of energy in it, stored, electrostatic potential energy. That location is high voltage, big positive voltage. Voltage is a measure of how much energy each unit of positive charge has at that location. It's literally energy divided by charge. Volts per coulomb. Coulomb being the unit of charge, the standard unit of charge. So a region that's chock full of positive charges. So you pile them up there. That's probably going to be high voltage, big positive voltage region, because a little positive test charge you put there is just going to want to leave. It hates being here. And if you let it leave and carry it, it will do work on you the whole way. And if you go off to way into the distance, the amount of work it did on you divided by its charge is the voltage that it left. So if it did 10 joules of work on you and it was 1 coulomb, then it was at 10 volts when you started the trip. Negative voltages correspond to places that positive charge likes to go to because it releases energy going to negative voltages. They're a net winner. If you have a positive test charge off in the distance and you start walking towards a region, oh, and it's pulling in there. Wow, it loves to be there, and it does 10 units of work on you, 10 joules of work on you, and it was 1 coulomb of charge. Well, then it went to negative 10 volts. That's less than 0 voltage. So how do you end up with places that have voltages that are less than 0? Put lots of negative charge there. It's a great destination for positive test charges. They love to go that way. Yeah, Kristen? Would it still be considered high voltage? I try to be careful. Not in my language, I'm careless, but on the paper, I'll be careful. If I say it's at high voltage, I'm going to say high negative voltage. I'll name it, because otherwise it's ambiguous or worse. Yeah. So you can have a high positive voltage is a place that's just chock full of positive charge, most likely. And there are other ways to make voltages, but that's the main one. And the details of the rest of the world around us matter, but get them out of here. If you have a whole lot of negative charge piled up, that's likely to be a very large negative voltage. So when they talk about high voltage power lines, they're meaning really high, big positive and negative voltages. Those transmission lines running across the countryside, if you watch as a function of time, you watch the voltage go surging up to 500,000 positive volts, and then surging down to 500,000 negative volts, and back and forth. Okay? Then next into electric fields. The zero-graphic copier, to really sort of understand how it manages to sprinkle charge onto this active photoconductor surface, you need to have some sense of electric fields, and electric fields are produced by electric charge. It turns out they're produced by things other than electric charge, as we saw later on. But what they do is they push on charge. So an electric field's job is to look for charge around and push on it. Charges are pushed in the direction of the electric field. So electric fields are a complicated conceptual object. They're structures in space that have an amount and a direction at every point in space. So if you have a positive charge here, living around that is this electric field, and at every point in space, you can go and look at it, and because this positive charge is making it, the electric field will point always away from the positive charge. Why? Because positive charges point in the direction that a little test charge, positive test charge, will be pushed if you put it there. And the strength of the electric field is how hard that positive test charge will be pushed. So around a real chunk of positive charge here, you're going to have an electric field that always points away from it, and it gets stronger as you get closer, and dramatically so, because this rule of the forces between charges going as 1 over the square of their distance. So the electric field near the positive charge is huge and away, and the electric field far from the positive charge is much more weaker, but still away. Negative charges have electric fields pointing toward them, because that's a place positive test charges would like to go. Circuits, and really the story of flashlights and the story of circuits. A flashlight, like almost any electrical device, uses the movement of electric charges, what is known as a current of electric charges, like a current in a river. This is current of charges, to convey power from a source to a destination. The source, in a flashlight, it's a battery, or multiple batteries. In other contexts, it can be other things other than batteries. But it's something that's brings energy into the system and provides it to the current. So current usually enters a battery with relatively little energy per charge, which is to say, at low voltage. Energy per charge is voltage. So if the charge enters the battery at low voltage, it's coming in with not much to work with. It goes through the battery, picks up energy per charge. Every charge picks up energy, so the amount of energy per charge is picked up. That's the increase in voltage. 10 volts, 20 volts, 100 volts. And the charge then leaves the battery, and it goes through the rest of the circuit. In the flashlight, it goes through wires and a light bulb. And in the process, it drops off energy. So its voltage is going downhill the whole time. And I've tried to convey a little bit these analogies between voltage and altitude of I don't know, bowling balls. You lift a bowling ball up to high altitude, you pack it full of gravitational energy. It's at high gravitational voltage. And then it rolls downhill, does things, and Rube Goldberg, whatever, and comes back. It's constantly it's losing that energy per bowling ball. And in the case of a real circuit, the charge is rolling downhill in voltage, and its voltage is going down and down and down. And it comes back to the battery exhausted with very little energy per charge left, low voltage, and goes through again, over and over. And the circuit's job was to convey power from battery to bulb, for example, in a flashlight, not to convey charge. So circuits are always literally a circuit, the whole loop, all the way around. If you make a circuit that only has one wire, the charge will go one way briefly, and then it'll pile up at the end of the circuit and have nowhere else to go, and therefore the movement of charge, namely, in other words, the current will decrease to zero, and no more power will make the trip. Yeah. Oh, I can't. We'll talk to me after class about that one. Okay. Let's see. So, anything else with flashlights? Oh, the idea of a short circuit. A short circuit was just this notion that if in a properly constructed circuit there is a source of electric power and there is a destination for electric power, something that's meant to consume it, a short circuit usually abbreviates the circuit, makes it short, and skips the designated power consumer. So instead of going through the filament of the light bulb to heat it up, the current jumps from one wire, leaving the battery, to the other wire, returning the battery. That's a bad idea, because now you've got the battery still supplying energy to every passing charge, but there's nowhere in this circuit is something that is supposed to consume that energy. And what happens is all the parts become electrical consumers, whether they like it or not, the wires. The battery itself can get hot. So the whole thing goes bad. In fact, actually, the grand disaster with the cell phones catching fire, you know the story. That's basically a short circuit. So, something, even it might have happened in the battery what's supposed to be the source of positive charge at high voltage got in contact with the destination of charge at low voltage, and the charge just started to go around and around and around, and things got hot. All right. Then on to magnetism and household magnets. So having talked about the story of electricity and electric charge, the two types of charge, positive and negative, really one's positive amount of charge, one's a negative amount of charge. We saw, there's sort of the same thing for magnetism. There's positive pole and negative pole, and like poles repel and opposite poles attract, and the forces get stronger as you get closer, and they go again as 1 over the square of the distance between them. But the weird thing that shows up is that there's no objects in nature that we know of that carry pure pole on them. There are objects that carry pure charge. A proton has pure positive charge on it. An electron has pure negative charge on it. Nothing we've ever noticed or found has pure north pole on it. The pole that shows up in nature always comes in equal and opposite amounts on the same object. So protons, for example, have a north pole and a south pole. They do have magnetic poles, but they're equal in amount and opposite, so they sum to 0. So proton's got no net pole, but it's got a north pole and a south pole. And that's part of the story behind magnetic resonance imaging, is the fact that all the protons in your body, for example, are all equivalent to little bar magnets, just teeny tiny quantum mechanical ones, which makes them more sophisticated to deal with. But the MRI machine is flipping those guys back and forth like compass needles, pointing with the field, against the field, back and forth. Bring the word field in. Magnetic fields are another story, and they're very much like electric fields. Magnetic fields point in the direction that a north pole would be pushed. So you have a north pole test charge, test pole. It would be pushed in the direction of the field, and the strength of the magnetic field is how hard that little test pole will be pushed. So we do have magnets, despite the fact that there are no objects that carry pure pole. There are lots of objects that carry dipoles, pairs of poles of equal and opposite amount. So a lot of bar magnets, a lot of the refrigerator magnets have at least 2 poles, one north, one south. Some of them have many poles. All permanent magnets originate, their magnetism originates down in the domain of the atoms themselves. The atoms are built out of electrons. Electrons are intrinsically magnetic. And if you they have north poles and south poles. If you have the right sort of chemical and material environment, you can end up with little patches of materials such as iron that are highly magnetic. They retain a lot of that electronic magnetism. The issue then is to make sure that doesn't cancel. It normally cancels in ordinary iron. You don't notice it's magnetic because that microscopic magnetism is all canceled away to nothing. But if you work on the shape of the crystals and stuff, and you apply a big external magnetic influence, you can line up all these so-called domains so that they all agree with one another instead of canceling one another. And you end up with materials that at least temporarily, maybe for a long time, have a very large effective pole at one end and a very large opposite pole at the other end. So that's all the permanent magnets that you've encountered in your life. They were materials that are intrinsically magnetic microscopically. It was canceling initially, but they were magnetized by exposing them to a really strong magnetic influence that got the poles to line up, and they are made of hard magnetic materials that tend not to forget. They tend not to go back to their original form because of internal behavior of the material. All right, that's just household type magnets. Then I went on to talk about electric power distribution, where I had to introduce the observation that there's a relationship between electricity and magnetism. Actually, it first showed up with the idea of electromagnets, that you can make a magnet using electric current. And that takes advantage of the fact that electric currents, that is, moving electric charges, are magnetic. They create a magnetic field. So I promised you for a while that electric fields and subsequently magnetic fields are real things that you can't ignore. You can't just say, oh, who needs that? They're really there. And part of one way you can see that is you can make an electric field without charge, and you can make a magnetic field without magnetic pole. And the way to make a magnetic field without pole, just move electric charge. Moving electric charge is magnetic. The other relationships like that appeared gradually over the later part of the semester were, so moving charge is magnetic, moving pole is electric. It's kind of symmetric there. And basically any changing electric thing creates magnetic fields, and any changing magnetic thing creates electric fields. So they talk to each other, those two fields. And this allowed for, in the case of electric power distribution, for the idea of a transformer. And a transformer, at its simplest summary, the transformer has electric currents in 2 separate circuits. 2 circuits that have no electrical contact with one another at all. So no charge ever moves between them. What moves is power. And how does it move? Because the current in one coil, so the transformer has two coils, basically, the simplest transformers. There are thousands of varieties, but okay, we're talking about plain vanilla transformer. It has two coils and a shared magnetic environment, which is typically created by iron passing through both coils. And when current flows through one coil, currents are magnetic. It magnetizes the core, and that magnetization changes every time the current changes in that first coil. So you send not just a normal current through it, but a current that's changing with time. And when you do that, you create a magnetic field that's changing with time, which creates electric fields in the second coil. And those electric fields in the second coil work to transfer power from one coil to the other. Basically, the electric fields that are produced by this process suck energy out of the original coil and the current in the original coil, and they give energy to the current in the secondary coil, the second coil. So energy is moving, no charge moves. And I mean, there are lots of details of transformers, but that's the main effect, is that the two coils talk to one another by way of magnetic field followed by electric field. Changing magnetic fields causing electric fields. And energy moves between them. All right? The value of using transformers, and the reason why we have an electric power grid that runs on alternating current is to use transformers, you have to use alternating current or something like alternating current. Why use transformers? Because we want to be able to generate and deliver electric power at relatively low voltages where it's safe. But if you're going to deliver a lot of power at low voltage, you need lots of charges carrying it. It's like you're giving small doses of energy to every passing charge in a circuit, so you need lots of charges. However, if you try to transfer power long distance as a large current of charges carrying not very much energy, you run into a terrible power waste problem. The power wasted in a wire is proportional to the square of the current in that wire. So it's to your advantage to lower the current in the wire if you're trying to go across the country with electric power. Send as little current as you possibly can. That way the wires won't consume it. But if you want to send a lot of energy, or actually a lot of power, using that pitiful little current, you better give every charge a lot of energy. And large energy per charge is large voltage. Okay? So that's why we have a high voltage, we have a whole voltage hierarchy in our electric power grid, where the voltage starts at moderate in the generator. It gets stepped up to very high voltage in the transmission lines across country. It then gets stepped back down as it works its way into cities, into communities, into neighborhoods. It just keeps working its way down until finally it's delivered at a voltage that won't fry you when you reach out and touch it. All right? Then on to radio. So having told you about electric and magnetic fields and the fact that they can create one another, I mean, the ultimate step is often to having them create each other and just become an independent agent and head off across space. And sure enough, that happens. Electric and magnetic fields, properly set up, can be the self-sustaining ripple that travels across space. And if there's nothing there, it travels at the famous speed of light, and it'll go clear to the other end of the universe. So all these radio transmissions people have been making over the years, they're all still traveling across space. They'll travel to the end of time. Off they go. So they are electromagnetic waves. And they have a certain structure dictated by the laws that govern how an electric field can make a magnetic field and how a magnetic field can create an electric field. So you end up with these waves. The simplest waves are these, the waves where I describe them as vertically or horizontally polarized. Where vertically polarized is by definition the electric field is vertical, then the magnetic field has to be horizontal. And these guys are they're waving together. They set off as a ripple in the third direction. That is, if the electric field is up and down and the magnetic field is toward you and away from you, a wave with that kind of structure can travel either to your left or your right, depending on the relationship between the orientations of the magnetic field relative to the electric field. Anyway, that's a vertically polarized wave. If you rotate the thing 90 degrees so the electric field's horizontal, now you've got a horizontally polarized wave. And there are other possibilities, it turns out, but those are the sort of a useful toolbox of electromagnetic waves. When they have long wavelengths and low frequencies, which means if they've got long wavelengths, they will have low frequencies. Why? Because as you watch the wave go by you, because the crests are so spread out, and the crests could be defined as electric field up as strong as possible, those waves traveling by, the crest won't pass you very often because this one goes by and the next one's like a mile down that way. It's going to be a while before it comes by. So associated with long wavelength, low frequency. But as the wavelength gets shorter, the frequency gets higher, and the name changes. It goes from radio waves to microwaves. And as it changes further, from microwaves, it goes to infrared light. And when it goes to infrared light, beyond that, visible light. And it comes in at the red end of the spectrum first, and as you get shorter, it goes to the violet end of the spectrum, and then off into ultraviolet. And as we saw later on, it goes then into X-rays and finally into gamma rays. And why do these matter? Well, I mean, you can use any of them for transmitting information. Some are easier to work with than others. We saw later on that a feature of quantum physics is that although these are waves, and people thought they were purely waves and nothing else, they have a particulate character too. When you create or absorb one of these electromagnetic waves, you do it unit by unit, where those units they're talked as quanta. And the name for a quantum of electromagnetic wave is called a photon. So it turns out that even radio waves, but certainly X-rays and stuff, are created and absorbed as photons, as units. And the energy in one of those packets, because electromagnetic waves carry energy. Electric fields and magnetic fields have energy in them. The energy in a photon is proportional to its frequency. The higher the frequency of the photon, the more energy it's carrying. So radio waves, tiny energy, can't do anything, barely noticeable. In fact, it's heroic effort to even detect that there's a photon character there. Visible light, now they can start doing stuff. They affect your eye enough that you can see. So they're causing gentle chemistry in your eye that allows you to see. By the time you get to ultraviolet, they can do pretty brutal chemistry. They can damage molecules forever. And that now is starting to be radiation that you want to be a little careful about exposing yourself to in great quantity. Certainly by the time you get to X-rays and gamma rays, this is not, they carry so much energy, they can do a lot of damage. You don't really want to be inundated by them. All right. Where next to go? With light, as it travels through matter in general, we saw that electromagnetic waves, they travel at the speed of light in empty space. But as they start interacting with material, passing through material, they start playing with it. The material plays with the light plays with the material, things happen. For one thing, the light slows down a little bit. In general, the denser the material it's going through, the more it slows down. So light slows down a little going through air. It slows down a lot going through glass and plastic and diamond and stuff. That slowing down had a couple of effects. One is that at the transition of going from fast to slow, there tends to be a reflection, partial reflection. It's an echo. This is the underlying physics of why there are echoes for sound, for any kind of wave. And so you get a little bit of reflection off of things like glass. On entering a material, so the part of the wave that doesn't reflect enters the material, but its path can change. It can bend, what's called refracting in going in. It tends, as it slows down, it tends to bend toward the perpendicular to the surface it enters, so that if it hits at an angle, hits a window at an angle, it tends to bend to dive more directly into the window. On the way out, it does the opposite. It bends away from as it speeds up, it bends away from the perpendicular and tends to go to a more steep angle as it leaves the window. So that effect, refraction is just kind of a novelty with respect to a window you barely notice, but if you start deliberately shaping a piece of glass, you can use it to do things like form images. So the camera lenses take advantage of this refraction process where light bends as it goes in and out of materials and changes speed. Another effect that occurs in that bending is associated with dispersion. Dispersion is the observation that the different waves with different frequencies, or equivalently different wavelengths, they travel at different speeds in materials. So in empty space, all electromagnetic waves travel at the full speed of light. In materials, they don't. And they travel slower, and their speed may depend on their frequency. So things like blue light tends to travel slower than red light in almost any transparent material. The details have to do with the nature of the material, and there are materials with what's called anomalous dispersion, where it goes backwards, where the blue part travels faster than the red part, but only over narrow ranges of frequency. In any case, the main feature of this is blues travel slower, and that means that not only if you wink a flashlight here with white light, and you send it through a pane of glass that is from here to the sun, 93 million miles thick, the light, when it arrives at the far end, the blue is going to arrive after the red. Instead of seeing a blink of white light at the far end, off in the distance, somebody out there will be looking and go, oh, here comes the red. Oh, now it's going yellow. Now it's going orange, yellow. It'll work its way through violet. It'll be slurped out in time. So that's one effect of this dispersion effect. But where it's more obvious is in the bending of light as light goes in and out of clear surfaces. The blues bend more. They slow down more, they bend more. So the blues and the red get spatially separated from one another. This gives you all these color effects with cut glass crystal or diamonds or jewelry in general. Different bendings because of the different speeds with which the waves travel. Trying to figure high points. I'm going to jump to 2 cents about semiconductor devices. We saw diodes, light emitting diodes. We saw transistors. They all have to do with the quantum arrangement of electrons in materials. If the electrons in assembling a material, the electrons bring the material to electrical neutrality, having filled these various quantum levels, quantum standing waves, only partially, so that this electron, one of the last electrons you put in there, could very easily shift into a different level that's available to it. Then the charges are mobile through the material, and you have a metal. If, on the other hand, in assembling the material, you've completely filled a band of levels, and the next electron that would go in there has to be in a completely different energy world, much higher in energy. Now it's an insulator or a semiconductor. And semiconductors devices are engineered by playing with this arrangement of how these levels fill. You get PNN type semiconductors, which I won't do now because it'll take too long. But take a look back at those. What I wanted to finish talking about was just the nuclear energy. The last things we talked about. The energy that's released in a nuclear explosion, the original nuclear explosions at least, is actually electrostatic potential energy stored in the repulsion between protons in giant nuclei. So the really big nuclei can release energy by disassembling themselves. They have so many positive charges so close that they have a net enormous amount of electrostatic potential energy that can be released by separating them. The little nuclei are different. The little nuclei don't repel each other so ferociously. So the act of assembling them, oddly enough, can release energy. The energy then is released it's not electrostatic energy, it's a nuclear energy caused by a new force, a nuclear force between the nucleons, the particles that make up the nuclei of atoms, protons and neutrons. The little nuclei, when you assemble them, that can release energy. Yes, you have to pay a little bit for the electrostatic repulsion, but there's a net release when they touch. And so the fission bombs use a trick, basically, to shatter a huge number of the giant nuclei at once and make a big kaboom. The thermonuclear bombs use that high temperature that's created in that process to bring together little nuclei and cause them to stick. Get them so hot that they can't avoid hitting each other. They hit and they stick, release more energy. Fortunately, you can also do this in a way, the first one, the fission process, in a way that releases energy in a sort of a gradual manner and doesn't blow things up, but rather generates nuclear power. It's got its issues, which I've talked about. And finally, the imaging. I'll just remind you that X-ray imaging uses photons, electromagnetic waves, to cast shadows of big nuclei like calcium. Lead for sure, but calcium is good enough. Imaging X-rays see bone by casting shadows. The calcium casts shadows. MRI is different. It identifies the presence of protons, of the hydrogen nuclei, the little magnets, by flipping them back and forth in the presence of a magnetic field. So they see different things. X-rays see bone very nicely. MRI sees tissue very nicely. They're complementary. All right, with that, thanks for sticking around, and I'll see you on a week from Tuesday.